Hi everyone, I'm back here with another video. And so in my previous video I gave a high-level overview of all the exciting things that happened on the open source side of large language models last year. So there was a huge amount of models being released on the Hugging Face Hub. It started with the Llama series from Meta in February. And now we have models like the Mixtral model, which is already at the level of GPT 3.5. So that's quite exciting to see. And so, in my slideshow, I gave an overview of how you could train these models, as well as how you can deploy them on your own hardware. But so this talk was still quite high level. So in this video, I would like to go a bit more in depth and really showcasing the code on how you can basically create your own GPT assistant at home. So recall that creating your own GPT or ChatGPT model, you could say, involves 3 big steps. Here, we actually show 4, but I will explain in a bit why there are actually only 3 main steps. The first one is called pre-training. So there we predict the next token. The model is asked to predict the next token based on the previous tokens. And so tokens, you can view them a bit as words. It could happen that the word might be split into multiple tokens. So typically, you will have more tokens than actual words. And so we do this on a huge amount of text from the web. So we collect millions and millions of text from the internet, GitHub code, all kinds of text in books and so on. And then we ask the model to predict the next word based on the previous words. And so we do this for several months. Well, actually, I don't do this, for example. This is done by large organizations who have the compute resources for this, because this is typically done on clusters of GPUs, done by organizations like Meta, for example, or Microsoft. And so the output of that is what we call a base model. So a base model is nothing more than a transform-based model that is really good at predicting the next token based on the previous tokens. And so, many of them are available on the Hugging Face Hub, luckily, so we don't need to do this pre-training ourselves. And so the one I will be using in this video is the Mistral 7B model from Mistral.ai, which is a French startup. And so they released a base model on the Hugging Face Hub some weeks ago. And so this model is just good at predicting the next words based on the previous words. But now involves actually the second step, and that's what I'm going to illustrate in this video. We're going to take that base model and try to make it a useful assistant, make it a useful chatbot. So we basically take our base model and then we do what we call supervised fine-tuning, or SFT for short. And so that's what I'm going to illustrate in this notebook here. And then the third step, which is actually shown here in 2 separate steps, is called human preference fine-tuning, where we're going to additionally fine-tune or supervised fine-tuned model on human preference data. With some newer techniques like DPO, which is short for direct preference optimization, we can actually combine these 2 in a single step. So that's why there are actually only 3 steps involved in creating a GPT assistant. And so there's actually a very nice open source repository created by Hugging Face that you can find on GitHub, called the Alignment Handbook, which was used to create such a GPT assistant, fully open source, based on the Mistral 7B model as well. And so, it involves some very nice scripts, both for supervised fine-tuning, as you can see right here, and then DPO, or direct preference optimization, to create your own chat model. And as you will see, the scripts are very readable, very nice as well for educational purposes. And so I basically took this run sft.py script and then copied it over here in this notebook, and then I basically will go over all the individual steps in doing supervised fine-tuning on any decoder language model. So all these large language models are the decoder part of the transform model. If you want to know more about how a transform model works, I have a separate YouTube video on that. You can actually run these scripts either on a single GPU or on 8 GPUs, depending on the hardware that you have available. in my case, I'm actually going to use RunPod, which is a GPU cloud provider. And so RunPod, yeah, there are many available. There are also other GPU cloud providers like Lambda Labs is another one where you can rent a GPU instance on the cloud, or Vast.ai is another one. And then you basically need to pay per hour that a virtual machine is running with a GPU attached to it. And so, yeah, for example, here in this case, Vast.ai provides RTX 4090 GPUs from NVIDIA. And that's also one I'm going to be using in my video here. So when you go to RunPod, you basically can select one of the available GPUs. And so in my case, I used an RTX 4090 with 24 gigabytes of RAM, because that's actually all you need, as also explained here, in order to do 4-bit training with the QLoRa method on a single GPU. That's what I'm gonna illustrate today. So yeah, RunPod is relatively straightforward to set up. You just need to hit deploy here, and then a pod is created for you. And yeah, it actually also comes with some pre-installed software. So for example, if you would click deploy here, then you can select what kind of software you want to be available already on that virtual machine. So in my case, I went for PyTorch 2.0 because that's the software we're gonna need, as well as the corresponding CUDA version, which is the underlying NVIDIA software used to run the GPU. And so then you get a pod, and then yeah, you can basically start it, stop it, and you are charged as long as the machine is running. So it's basically renting it. So in this case, I'm going to start this instance. So I went for an on-demand instance, which means that the machine is only assigned to me, which has a higher price compared to spot instances, which might disconnect, similar to the ones of the free version of Google Colab. Then you can click on connect, and then you can go to Jupyter Lab, which is like a Jupyter notebook environment. And so basically I just wrote an initial notebook here in Google Colab, and then I downloaded it, and then I uploaded it here into this virtual machine. So one of the first things I'll always do to make sure things are running fine is checking whether a GPU is available. So that's the case. We have an NVIDIA RTX 4090 in this case with 24 gigabytes of RAM. And another thing I check is whether PyTorch recognizes the GPU. So for that you can do torch.cuda.is available, which should print out true. All right, so everything is fine here. So we'll basically go over all the steps in going from a base model to a useful assistant with supervised fine-tuning. And so the interesting thing here with the second step, supervised fine-tuning, is that we're still going to use the exact same loss function as used during pre-training, which means we still are going to train the model to predict the next token based on the previous tokens. However, in this case, we want the model to generate useful completions given some instructions. Like for example, if an instruction would be give me 10 things to do in London, then it should generate a useful completion where it gives recommendations regarding things to do in London. Or for example, if an instruction would be how can I make pancakes, then we want the model to generate a completion that involves a recipe for pancakes, and so on. So yeah, that's actually what we need to do supervised fine-tuning, and that's why it's called supervised, because yeah, we actually would need some label data here where we have pairs of human instructions with corresponding human written completions that we want the model to generate. And so yeah, OpenAI, for example, they have hired human contractors for this in order to generate these completions given instructions. And so there are several supervised fine-tuning datasets available on the Hugging Face Hub as well. So the Hugging Face team behind the alignment handbook has collected some awesome SFT datasets, which you can use to create such an instruction-tuned model. And so the dataset we're going to be using in this case is the UltraChat 200K dataset, which is a collection of 200,000 human instructions with corresponding completions that we want the model to generate. And this was actually also used by the alignment handbook, because yeah, my notebook is actually a full copy of this script here. All right, so yeah, the first thing we're gonna do is install the required libraries. So I'm gonna use quite some Hugging Face libraries in this case. So we will need the Transformers library in order to load our Mistral base model. So the Mistral 7B model, which we can fine-tune on a single GPU. Then I'm gonna install the datasets package in order to load this UltraChat dataset. Because the UltraChat dataset yeah, can just be loaded in 2 lines of code using the datasets library. And then I'm also going to install some libraries to do fine-tuning in an efficient way using the bits and bytes and PEFT libraries. I'm also going to explain in a bit what these mean. And then finally, I'm also going to install TRL, which stands for Transformers Reinforcement Learning, because that one has a very handy trainer class for doing both supervised fine-tuning and reinforcement learning on top of transformer-based language models. So in this case, I will have to install these packages here on that machine. And then a final library which we also are going to install here is Flash Attention. Because yeah, these transformer-based models, they use a mechanism internally called attention, because the original transformer paper is called attention is all you need. And yeah, attention is quite a heavy operation. And so Flash Attention speeds that up. So Flash Attention is a library developed by some folks at Stanford University, which will basically drastically speed up the computations of the model, which will make our training faster and more efficient. And we're gonna use the second version called Flash Attention 2. An important thing to note here is that yeah, Flash Attention 2 only works on the newer generations of NVIDIA GPUs. So these include NVIDIA A100, the one that I'm going to be using in this tutorial, the RTX 4090, and so on. These have the Ampere architecture, which support Flash Attention 2, because the older generations, like the Turing architecture, like a NVIDIA T4, for example, does not support Flash Attention 2. So that's one thing you would need to adapt if you're running on an older GPU. And another thing is that we're going to train our model using bfloat16. bfloat16 is a format developed at Google Brain. It's basically a format to do yeah, fine-tuning in a stable way of neural networks, because previously people were using floating point 16, also called half precision. But yeah, that one is known to have some stability issues and rounding errors during training. So it's definitely advised nowadays to use bfloat16 as format for training. But also, I'm going to explain that later on in this video. So I'm just going to install Flash Attention here. And then, yeah, the first thing we're going to do is we're going to load the UltraChat dataset from the Hugging Face hub. So this is just 2 lines of code. And so, as I said, what we're going to need to do supervised fine-tuning is instructions with corresponding completions. And we simply are going to train the model to predict these completions given the instructions. And so, yeah, you might wonder how the format looks like for such a data set, because it could happen, for example, that you want to create your own chatbots. So in that case, the format that you would need to prepare looks like this. So basically, for every single example in your data set, you would need to have this messages column. And so the messages are basically a sequence of messages between a human and a chatbot. And this is what we're going to train the model on. So it's basically a sequence of instructions followed by a completion and then followed by another instruction, and so on. So we call these multi-turn conversations. And yeah, here I can actually already show how that looks like. So basically, every single training example has such a messages key. And so the messages is just a list of dictionaries where every dictionary is a single message in the conversation. And every message always has two keys, namely a role, which indicates whether it was a human specifying that message or whether it was a chatbot or an assistant, and then the actual content of that message. And so here, for example, I'm printing out the messages of the first training example. And so as you can see, we start with a message from a human because the user role is the human. These instructions apply to section-based teams. What team version am I using, and so on. And then we have an assistant message where we have the completion, you could say, of that instruction. And then we have another message from a user: can you guide me through the process of enabling the secondary image hover feature? Yeah, in this case, it's not about things to do in London or pancakes. In this case, it's actually about some features in the Shopify app. And then we have here the corresponding completion of the model, given that instruction. So yeah, if Shopify, for example, would want to create their own custom chatbot, this is how the data should look like. So in this case, yeah, it has loaded the entire data set. Yeah, for debugging purposes, I've just included this line here to make sure that we only are going to use 100 rows of both training and testing, and then we can scale it up later on once that works on the small scale. It's one of the many things I learned from the blog posts from Karpati on yeah, recipes for training neural networks, and yeah, one of them is to start small and scale up later on. I definitely recommend to check out that blog post. And so yeah, every single training example has this messages key. The prompt and prompt ID are actually not that important. So it's basically a sequence always of human followed by assistant and so on. And so the first thing that we will need to do is applying the chat template, but for that we need a tokenizer. So that's what I'm doing here. So a tokenizer is the thing we need to prepare the text, so the messages for our model, because a transformer-based model doesn't directly take text as an input, but rather something called input IDs, which are the integer indices in the vocabulary of a model. That's of course a lot of words. I also have a separate YouTube video on that if you want to really know how a transformer works, both at inference time and training time. In this case, I'm going to keep it short. But basically, if we look, for example, at this Mistral 7B model, the base model, you can go here to the tokenizer file, which is the vocabulary of the model. And so the vocabulary is a mapping between tokens and corresponding integers. And so these, you could say, are all the individual tokens that the model knows and that it can predict as next token in a sequence. So the tokenizer is used to split up the text into smaller pieces called tokens. And then we basically are going to do a lookup into the vocabulary of our model to then turn each token into a corresponding integer, which are called the input IDs. So I can actually illustrate that here. Let's say I have the text, hello, my name is Niels. Then you can do the following, tokenizer.tokenize text. So this is going to print the tokens. And as you can see, a single word like hello might be tokenized into 2 separate tokens. So we typically have more tokens than we have words. And then we are going to turn every single token into a corresponding integer by looking up that token. So in this case, for example, this token, if I would go to the vocabulary and look that up in the vocabulary, then it's correspond to integer 6312. So for that, you can call the tokenizer.convert tokens to IDs method on that, and then this is what we get out. And this is actually what we're going to feed as an input to our model. But yeah, you can actually do this in a single line of code because the Transformers library makes this very easy. And as you can see right here, there's also a special token being added at the beginning, yeah, which is typically called the beginning of sequence token. So you can actually convert that back into text using the tokenizer.decode method. Let's see how it looks like. So yeah, we have added this special token right here. Yeah, a special token is mainly used to indicate to the model that a new sequence is starting. So yeah, in this case, we load the tokenizer that corresponds to this base model, and then we are going to add some things. So one is a padding token ID, because by default, the tokenizer of a base model doesn't have that set. So it doesn't have a pad token set or a padding token ID, which is the corresponding integer index in the vocabulary of the model. And that's because during pre-training, we don't need to pad the text to the same length, because we can just chunk the internet text that we have. However, during supervised fine-tuning, we will have these messages for every single training example. And so these messages, they all have a different length. Like one conversation could have 500 words, but another one could have 600 words and so on. But yeah, typically we train neural networks on batches of data of the same length. So that's why we are going to pad them up to the same length and truncate sequences that are simply too long. So that's why we're going to set here a pad token ID. And this is basically going to allow us to then do the following. So if you would have the text hello world, then you can do the following. So you can call the tokenizer on that text, and then you can set, for example, padding equals max length with a max length of, let's say, 30 tokens. And then, yeah, we will have input IDs that are padded up to that length. But so, yeah, that's why we are setting the padding token, and we're going to use a model max length here of 2048 tokens. So all of our messages of all the individual training examples will all be padded or truncated to the same length of 2048 tokens. So that's why we're setting the model max length attribute here. And then the final thing which we are also setting is the chat template. So the chat template is basically a way to format all of our messages for the model before tokenizing it. So yeah, in Hugging Face Transformers, you can do this by defining a Jinja template, which basically defines how that sequence of messages from users and assistants is turned into a tokenizable string for the model. So after applying the chat template, we are going to then split them up into tokens and turn them again into input IDs. So yeah, that's actually the first step after defining the tokenizer, is to apply this chat template to all of our messages of our dataset. But in order to better understand this chat template, I'll quickly jump here to Excalidraw to just explain you the ID. So basically, if we would have, for example, this conversation here, a list of two messages in this case, one with a user role and one with the assistant role, where, for example, the user asks, "What do you know about Belgium?" and the assistant replies, "Fries, chocolate, and beer." Then if you would call the tokenizer.apply chat template method on that sequence of messages, which is what we're going to do here as well, apply chat template, then it's going to basically turn that into this string. So as you can see right here, it adds some special strings here indicating the start of a user message, as well as indicating the start of an assistant message, as well as adding a end of sequence token to the messages as well. So you can actually see that here. So if you would instantiate here a tokenizer from the Mistral 7B model with that chat template being set, and these would be your messages. If you then call the apply chat template method on that, then this is how it looks like. You can actually print out the raw string by calling this method. So this is basically how each of the sequences of messages is going to be formatted for the model before tokenizing. Because after this, we are basically going to do again tokenization, so which means splitting up the sequence into a set of smaller pieces called tokens, and then again we're going to look up those tokens in the vocabulary of the model, turning them into integers. So yeah, I actually had to explicitly set tokenize equals to false here to just illustrate you this. And then, yeah, if you would call it by default, it will turn them automatically already into input IDs. And so, yeah, for example, this is a special token indicating the end of a sequence. And this is also going to make sure that our model will be able to generate an end of sequence token, which will mean that we are going to stop generation. And this is actually also how ChatGPT works. So basically, whenever the model generates an end of sequence token, we know that the model needs to stop generating new text. So luckily, the Hugging Face datasets has some very nice tooling for not only loading datasets from the Hugging Face hub, but also processing them in an efficient way. And this is all documented here, but in this case, we are going to use the .map functionality, which takes in a custom function, could be anything, and then you can apply it very efficiently in a parallelized way. So that's also what I'm going to do here. So we are going to call the Tokenizer apply chat template method on the individual messages of each training example. So as you can see right here, we are specifying tokenize equals to false. So we are not going to tokenize yet here. That's actually going to be done by our trainer class later on internally. So yeah, here we define this apply chat template function. We provide it to the map method. This is going to allow us to do this very efficiently on all the available CPU workers of our machine. So in this case, we have 256 CPU workers, which is of course much more efficient to leverage rather than just a single one. So that's multiprocessing to do the mapping in a very efficient way. And then we're also going to remove the existing columns. So let me just call this right here. We get a warning here saying that the number of processes is smaller than the number of rows in our dataset. That's because we are running this on just a small scale of 100 rows for the training split and the test split. And then this is how a random training example will look like after applying the chat template. So as you can see right here, we have added these special strings followed by the end of sequence token as well. And we also added here a system string. So system role, you could say, basically will indicate to the model how to behave. So the ChatGPT, the chat completions API of OpenAI, for example, also allows to set system prompts, which basically are kind of a meta prompt indicating to the model how to behave. But for our training purposes, we are going to set the system prompt to an empty string for all of our messages. We are only going to have user messages and then assistant messages right here. So yeah, this is how a single, as you can see, it's quite a lot, but yeah, we have room for 2048 tokens. All right, so once we have done that, it's time to define the model arguments. And so yeah, here I need to explain a bit how exactly we're going to do the fine-tuning, because there are various ways of fine-tuning neural networks. Typically, what people have been doing until recently is what we call full fine-tuning, which means that we are simply going to take the weights of our pre-trained model and we're going to simply update them all. So that's called full fine-tuning. And this could be done in various precision formats. So this basically means the number of numbers behind the comma. So for example, float 32 would mean that we would store each of the single parameters of our model in 32 bits or 4 bytes, because a single byte is 8 bits. So full precision is of course also quite memory intensive, because you need 32 bits or 4 bytes per parameter to store every parameter. So yeah, people have developed some more memory efficient formats like mixed precision, which combines float 32 with float 16, which is called half precision, or nowadays we would use bfloat 16, which is a more stable format developed by Google Brain. However, the problem is that in this case we are dealing with a large language model that has 7 billion parameters. So 7 billion parameters. For example, if we would use float32, which is a full precision format, then we would require 4 bytes per parameter, 32 bits, which would mean 28 gigabytes of GPU RAM. And that's to only load our model into our GPU, which is already more than what we have, because in this case, for example, we have an NVIDIA RTX 4090 with only 24 gigabytes of RAM, so that's not feasible. And then another thing is, during training, we not only need to load our model into the GPU memory, we also are using an optimizer, like for example Adam W, which is a very popular one, used to fine-tune transformer-based models. But that one also requires us to store the gradients of the parameters as well as the optimizer states of the parameters in our memory, which simply make it infeasible, because there's actually a formula on that. Approximately, when you're training in mixed precision with the Adam W optimizer, you would roughly require about 18 times the size of your model in terms of parameters. In terms of gigabytes of GPU RAM. So if you have a 7 billion parameter model, for example, times 18, that would require 126 gigabytes of GPU RAM. That's just not feasible at all. And here we're only talking about a 7 billion parameter model. This is actually all explained in much more detail in this very nice guide in the Hugging Face docs. That's what we are calling full fine-tuning. So this is actually also illustrated here. So that's simply not feasible with a 7 billion parameter large language model. Luckily, there are some newer methods being developed. And so one very popular one is called LoRa, which is short for low rank adaptation. So this is a method developed by some researchers at Microsoft. LoRa is the idea of basically freezing the existing model. So we're not going to update our pre-trained weights. We're going to leave them untouched. And we are only going to add a few adapter layers on top of that base model, which we're going to fine tune. And so as we have much fewer adapter parameters, this is becoming much more memory friendly. LoRa is one that is currently very popular, both for fine-tuning large language models, but also fine-tuning text-to-image models like Stable Diffusion. So this will require us to only have optimizer states and gradients for our adapter layers on top of our base model. So this is also explained here in this figure. So for example, if our base model would be a transformer language model and we load that in 16 bits or half precision, which could be bfloat 16, for example, with full fine-tuning, we would also need to store the optimizer states, which are typically stored in 32 bits, which would make it not feasible at all. However, with this LoRa method, you are only going to add a few adapter layers, which we are going to train still with 32 bits for the optimizer states and then 16 bits for the adapters. That's already making it more feasible. And so LoRa is what we call a PEFT method. So PEFT is short for parameter efficient fine-tuning, because we're doing the fine-tuning in a more efficient way. And that's why Hugging Face has developed the PEFT library, which includes several of these techniques like LoRa, enabling us to fine-tune these giant models on consumer hardware. And luckily there's now an even more efficient method, which combines the LoRa method with quantization. So quantization, actually I've already explained a bit what quantization is, because for example, if you go from 32 bits to 16 bits, so from full precision to half precision, that's already a form of quantizing. So you're shrinking down the size of your model by using fewer bits per parameter. And nowadays, we have even more efficient quantization formats like 8-bit per parameter or only 4 bits, which is half a byte per parameter. There are several of these quantization techniques available, which significantly shrink down the size of our model while keeping the performance basically the same as full precision, which is the impressive thing about it. One such a library is called Bits and Bytes, which has an integration with the Transforms library, and which we are going to use in this tutorial to quantize our model to only 4 bits. And so, yeah, the idea of combining quantization with the LoRa method of only adding a few adapter layers and keeping the base model untouched is called QLoRa. So we have a whole blog post on that if you want to know everything about it. But basically, you only need to define a couple of things here. We are going to instantiate such a quantization configuration. So in this case, we're going to use the bits and bytes quantization method to load our base model in 4 bits. And so the adapter layers are still going to be trained in bfloat 16, so 16 bits per parameter, as well as for their gradients. And I think for the optimizer states, 32 bits are going to be used. But so, yeah, if you do the math here, 4 bits per parameter, so half a byte, for a 7 billion parameter model, that would only require 3.5 gigabytes, which to load the model, which, yeah, makes it a lot more feasible. And that's also why the alignment handbook, for example, has these scripts available for doing QLoRa, which, yes, 4-bit training on a single GPU. So yeah, here we basically specified how to quantize our base model. These are some specific hyperparameters regarding bits and bytes. And then, yeah, we will automatically place our model here on the available GPU. We only have a single GPU available. We also specified to use flash attention 2 in this case, in order to speed up the attention computations of our model, as I said earlier in this video. And yeah, based on that, we actually have everything we need to define our model. The next step is then to define the trainer class. And so that's why we're going to use the TRL library, which provides some very handy classes for training. So both for supervised fine-tuning as well as for the human preference fine-tuning stage, which I'm going to explain in a different video. So yeah, the SFT trainer class is what we're going to use. And so it makes it very easy. It's basically inheriting from the trainer class in the Hugging Face Transformers library, but is specifically optimized for doing supervised fine-tuning. So yeah, here we are basically defining the training arguments, which are all the hyperparameters regarding training. So here, for example, we specify bfloat 16 equals to true, because we're going to still use bfloat 16 for training our adapter layers, while keeping our base transformer model in 4 bits. Yeah, we also specify some other techniques to make the training more efficient, using gradient accumulation and gradient checkpointing. Those techniques are also explained in this documentation here, efficient training on a single GPU. I refer to that documentation if you want to know more about those methods. We specify the learning rate, the learning rate scheduler, and so on. And we are going to train over the dataset only a single time, so a single epoch in this case. And yeah, the batch size that I successfully used was a batch size of 2. I was not able to scale it up further on a single RTX 4090. Of course, if you would have an A100, for example, then you can easily set this to a batch size of 8 or more. And then you can also specify, for example, to push your model to the hub after training, or for example, during training after every few steps. Next, we are going to load the LoRa configuration. So this is available in the PEFT library for parameter efficient fine-tuning for the QLoRa method. So yeah, these are some hyperparameters regarding the LoRa method itself. I refer to the documentation on that in the PEFT library. But basically, we are going to place these adapter layers on top of the projection layers inside the attention layers of the Mistral base model. So if we would go into the source code of the Hugging Face Transformers library and we go to the Mistral model, you will see that in the Mistral attention class, the projection matrices are called QProjection. So this stands for query projection, keys and values, and then output projection. And so we are going to place our adapter layers for doing LoRa on top of these linear layers. That's why we're specifying here target modules equals those names. And then it's just a matter of instantiating our supervised fine-tuning trainer with the model ID. So the model ID is going to be the Mistral 7B model. So the SFT trainer class is basically going to automatically load the weights of the model into, I first need to run this cell here, into our virtual machine, as you can see right here. So here it's loading this file from the hub. And so the original base model, the Mistral 7B model, if you check the original tensor type, so the original model was already trained in bfloat 16. So 16 bits per parameter, which means 2 bytes. So that means that roughly the size will be 14 gigabytes, because 2 times 7 is 14. That's how you can know the size of the model. But so we're providing here our PEFT configuration, so our LoRa configuration, which will mean, as well as these model arguments, which will mean that we are going to turn our base model into 4 bits using bits and bytes, then adding the adapter layers using PEFT. And then we basically provide our training data sets where we apply the chat template for. We also provide the tokenizer, because the tokenizer will then be used internally inside the SFT trainer class to turn these messages into input IDs. Because that's actually also explained here. So if we would have, for example, this sequence of messages and we apply the chat template, then we get this. And so then the next step is to do the tokenization. And so that's going to happen internally inside the SFT trainer class. So tokenize, which is then going to look something like, well, let's say that this, for example, might be a single token. And then this might also be a single token, but then, for example, what might be tokenized into 2 separate tokens, and so on. So then, we basically are going to look those up into the vocabulary of the model. And then we have our input IDs, which are these integer numbers, which are going to serve as the input to our transformer decoder, which is the Mistral 7B model. But of course, ChatGPT, Mistral 7B, Llama, and so on, they all have the same architecture. They are all transformer decoders. And then the model will basically be trained to predict in the next token, but it will basically predict the next integer, because the model only sees these integers. So the labels here, they are created automatically based on the input IDs. We just basically copy paste them right here, and then we need to shift them one position like this, because the model basically, for example, when it sees token with ID 523, then it needs to predict that the token that after that comes is the token with ID 28,766, and then for the token with ID 28,766, the token with ID 1,838 should come, and so on. And so here, the predictions of the model and the labels, we're gonna compute the cross entropy loss between those, and that's actually how we are going to update the weights of the adapter layers. And then finally here at the end, we add a end of sequence token, which will probably have token ID 2. So that means that the model will then be trained to predict after the token with ID 13, it should predict the token with ID 2. So that's actually how a transformer decoder is trained. But if you would go into the internals of that transformer decoder, it would look like this, but I would probably need a whole separate video on explaining like the actual internals of such a Mistral 7B model. Alright, so in this case it's still loading the weights. As you can see, it takes some time. But after that, one other important thing here is that we're specifying packing equals to true. That's another feature of the supervised fine-tuning trainer class. So packing basically means that we can pack together several shorter training examples into one long sequence in order to increase the training efficiency. Basically, it will allow us to train faster using this trainer class. So it's definitely recommended to use packing equals true during supervised fine-tuning. And then, there are also some other features available in the supervised fine-tuning trainer class, like you can also specify to only train on the completions rather than the instructions, because in this case, the model will actually also be trained on the instructions, which might not be ideal. Like, for example, you only want the model to learn to generate the completions given the instructions rather than also learning to generate the instructions themselves. And so, there's support for flash intention too. And then a recent thing that we also released is the integration with Unslot, which is a separate library built on top of Hugging Face libraries to do the fine-tuning of these large language models in an even more efficient way. They have developed custom CUDA kernels for models like Mistral and Llama to do the fine-tuning even faster. And so this is now also available through this integration. So it's basically just swapping your Mistral model with a fast Mistral model, for example. But I'm not going to use that in this tutorial. It's just something that you may find interesting. So, and then it's just a matter of calling the trainer.train method, which is going to train our model. And you can actually also specify a certain logging tool in your training argument. So, for example, if you want to log to a tensor board, or you want to use weights and biases to see your training run, that's also integrated here. And after you have done the training, so I'm not going to wait for this training to finish. You can save the model by calling the trainer.save model, where you specify a certain directory to save the weights of the model. Well, we're actually only going to save these adapter layers, which are just a few megabytes compared to the 14 gigabytes of the base model. And then, for inference, once we have trained our adapter layers, it's just a matter of calling the from pre-trained method on the auto model for causal LM class. And so also at inference time, so when you're generating new text with your trained model, you can specify to load the model in 4 bits. So this will automatically load both the weights of our base model as well as the adapter layers, thanks to the PEFT integration in the Transformers library. You can actually read about that in the PEFT documentation. So this is integrated in the Transformers library. So it basically means that if you have, for example, this repository, which only contains the adapter layers, if you go here, for example, to the files and versions tab, you will see that only the adapter weights are saved, which is only 6 megabytes. So that's, really a very small file together with the configuration. The Hugging Face Transformers library will know that it should also load the base model based on the adapter layers. And that's because in the configuration here, we specify the base model name. In this case, it was an OPT language model, but in our case, it's going to be the Mistral 7B model. So, okay, it seems that training has finished here, and then you can save the model. And then for inference, so there are actually 2 different ways. One is by doing it like here, so where we are going to actually instantiate the classes ourselves by calling the from pre-trained methods. And then let's say this is what we're gonna want to test at inference time. You can add, for example, a system message to indicate to the model how to behave. So in this case, we add, "You are a friendly chatbot who always responds in the style of a pirate." And then, for example, use a message asking how many helicopters can a human eat in one sitting. And then it's just a matter of calling, again, the apply chat template method on those messages, which is going to turn it into that formatted string, which we are then going to tokenize and turn into input IDs. That's all handled by the apply chat template method here. And then it's just a matter of calling the generate method, which is going to then auto-regressively generate one new token at a time by always feeding in the next predicted token back as an additional input to the model. And yeah, there are various ways to do autoregressive generation in Hugging Face transformers. There's actually a whole blog post on that, which I highly recommend to check out, because there are various different decoding ways. One is called greedy decoding, which means that we are always going to take the token with the highest probability at every single time step. But there are some fancier methods like beam search and sampling, as we're using right here. And so the model basically generates some new token IDs, which we then can turn again into actual text by looking them up into the vocabulary of the model. And in this case, for example, it has generated, I'm not sure, but let's say the average human eats 10 helicopters in one sitting. So that's quite interesting to see. But of course, I only trained this model on 100 rows. I saw that it was still generating some follow-up user messages and then assistant messages, which is still an artifact from pre-training. If you would do the full supervised fine-tuning on the entire UltraChat dataset of 200,000 examples, it would basically generate an end-of-sequence token, and then it will basically stop generation. So yeah, that's about it. These are all the steps involved in doing supervised fine-tuning of any large language model available in the Transformers library. So yeah, I would say if you want to do the fine-tuning on a single GPU like I have done in this video, you could do it either in a notebook or simply go to the alignment handbook, which has these very handy scripts. These also work out of the box on multiple GPUs. Then it's leveraging DeepSpeed, which is a framework developed by Microsoft to do fine-tuning on distributed environments in an efficient way. And yeah, it comes with corresponding recipes, which are like configurations regarding hyperparameters of the training. So this is actually where I got all these information from on setting the appropriate learning rate, setting the appropriate target modules for the LoRa method, and so on. So yeah, this is contained in the recipes directory. So yeah, that was step 2, supervised fine-tuning. And then in the next video, I'm gonna go to the final step of creating a ChatGPT at home, which is DPO, or direct preference optimization. So stay tuned for that. Thanks for watching.